Okay, so let's start. So that's where we are. We're talking about semi-supervised and unsupervised learning with EM. So let's start actually with some administration. So remind you, most of you are doing projects. So if we haven't discussed your project yet, please come today or tomorrow. Hopefully that will be enough to talk to all the teams. I think everything was on Piazza and on the website, so you should know deadlines, posters, and so on. No class on Wednesday, so Wednesday is running as a Friday. I assume some of you have Friday classes. If not, you have time. But we're going to have office hours. So the TAs will have office hours Monday to Wednesday. Check to make sure that everything runs as usual. The other thing to remind you is that there's going to be an exam. I already showed this before. We still don't have the room, but I assume we'll have it at some point. Questions on any of these? No questions. Okay, so let's move on. So where are we? So in fact, before we get to where we are, I want to remind you. So we're talking about probabilities. Hopefully, we ask you enough questions already, so everything important is kind of at the top of your head now. I want to remind you one notion of expectations that, again, you've all seen, but we're going to use it a couple of times today. So we have a random variables that take k values. The values it takes are x1, x2, up to xk. The probabilities it takes these values are respectively p1, p2, up to pk, where the sum of the pi's is 1. Therefore, the expectation of x is this sum over I runs from 1 to k, the probability that x takes the value xi times the probability times the value xi. So the sum pi xi I runs from 1 to k. And we're going to see this in a couple of ways. That's one important thing to understand what is expectation. Basically, weighted average of the values the variable takes. And the other important property is that expectation is linear. We're going to use this. Okay, so where are we? So we talked about naive Bayes. And we're going to use this as a way to, as the technical tool, or the probabilistic model, if you want, for our expectation maximization algorithm, for the EM algorithm, which is the main tool for unsupervised or even semi-supervised learning. So we're assuming that we have naive Bayes, that we can use naive Bayes for learning to decide between two labels, N and V in this case. So the examples that we are given are, I'm sorry that I'm loading here the index N here, x1 up to xn examples, and the labels are also called N and V. So using naive Bayes is basically this simple thing when we write all the statistics in two columns, the N column and the second label, the V column. And then once we're given an example, we care about some of the statistics, not all of them, only those that are present in the example. So for example, here, given that the example, the feature values are x1 up to xn, we care about p of x1 given the label, p of x2 given the label, p of the last feature given the label, and so on. And once we compute the probability of the label given the example, the two labels given the example, we compare the value and we're done. So we gave this example here, where the model was computed given the examples that were given, only 10 examples. These are the model parameters that we got. Two types of model parameters, or the priors, if you want, P of n and P of v, and then the P of xi given the labels. And this allows us to compute the probability of each example and make predictions. Then we ask the question, what happens if in addition to these 10 labeled examples, I also give you a lot of unlabeled examples? And this is really an important example because it's realistic. I mean, in many, many situations, it's very easy to get unlabeled data, not so easy to get labeled data. So how do you gain from this? And basically, we discussed this and we said, well, we kind of have two options. One option is just use it. Make the prediction on this data. You can, because you already have a model. We just showed how to make prediction using the model. Label these 100 examples. And now you have 110 labeled examples. Yes?
So how is your model going to be different than if you just use the original 10?
Okay, first of all, it will be different. The question is because you labeled the data, the data had other active features. So if you can just take an example and see that if you had even one unlabeled example, label it, and redo the statistics, you're going to get somewhat different statistics. Because maybe previously all the features, all the examples had x1 as 1, and now no example has, in the unlabeled data, no example has x1 as 1. Some of the statistics are going to change. But you're right in the sense that you have not added any information, right? Modulo, again, new statistics on when active features are active, when features are active together and so on. But your intuition, I guess, is that maybe we're just adding noise here, right? So we don't have any information. And therefore, this by itself is not a good idea. You can actually try it because you're playing in a very similar scenario in your homework. So maybe a better idea is not to believe all the 100 predictions, but rather believe some of them. And if you want to believe some of them, you have to have some criterion for how to choose this sum. And there are several ways people can do it, and in the homework we suggested you two. One of them is a threshold-based. Just choose those 100 predictions that you're confident about. Could be either positive prediction that you're confident about or negative prediction that you're confident about, but disregard those that are in the middle. Or you can just take the top sum under the assumption that your model gives relatively solid confidence when it predicts. Choose the top few and say, I'm very confident about these. I'm going to incorporate them and keep on going. So that's one way of doing it. A second way is to actually use fractional labels. So we know that given a prediction, Pn of x or Pv of x, we can compute, we know that the probability that an example is Pn is an n example is this, and the probability that it's a v example is this. We can actually assign these two numbers to the example. No one said that the label has to be an integer, right? Think about the naive Bayes algorithm and the way it works. He doesn't care whether the label is fractional. The same algebra that you're doing to compute the parameters, you could do also with fractions. So that seems like a more principled way. In fact, if your model is correct and Pn of x is indeed the probability of this example belonging to n, This is the best thing you can do. This is the right thing. Right? And notice that it kind of generalizes option one in the sense that if you have an example where you're not so confident about it, which means P of n and P of v are about the same, essentially, this example will not be taken into account when you compute the parameters, right? Because it will appear in about the same way on the left column that I showed before. It will contribute to, in the same way, to the left column and the right column. So essentially, it won't be taken into account. If it's exactly half, you can clearly see that you can just eliminate it. So this is a good thing to do. But let's just think again. What happens once we do this, right? So let's assume you've done that. You've labeled each example in a fractional way. What are you going to do now? Yeah?
Maybe take those with like 95% or higher confidence?
Actually, you don't need to, because already those that have close to half, they don't matter, right? Because they contribute in the same way to the n and v. So you could take all of them with this. But let's assume you've taken whatever you've taken. What are you doing now? What's your next step? You've labeled the 100 examples, and what does that mean?
Run all of them when you're building your model all bunch again.
Basically, you're recomputing the parameters again, right? So essentially, you take these 110 examples now, and you estimate again what is P of n, what is P of v, what is P of xi given n for all i's, what is P of xi of v given all i's, and so on, right? So you're basically recomputing the parameters with the new label data, and you can iterate, right? Because once you've computed this, and you go back to make predictions on your data, you're going to get somewhat different predictions, right? You're not going to get the same predictions that you started with. So you can iterate this algorithm. Everyone sees that? Okay, and in fact, that's a very important algorithm that is the answer to the question. Okay, here I'm just summarizing what we've done, so let me skip this because we already saw this. This really is the answer to my question, what happens if instead of 10 labeled examples, we start with 0 labeled examples? Because we're going to do just what we just described. We're going to start with some parameters, compute these fractional labels, and keep on going. And this algorithm is going to be called the EM algorithm, and we're going to write this in a more explicit way. So what is EM? So EM really is a class of algorithms, and we're going to see today 2 instances of the EM algorithm. It used to be to estimate probability distribution in the presence of missing attributes, or models, if you want, in the presence of missing attributes. And the most interesting case is where the attribute that is missing is the label. You just got the example, you don't see the labels. It requires assumptions, right? Because, as I said before, if the Pn and the Pv are correct, everything we're doing is the right thing to do, which means that we have to make some assumption on the family of probability distribution that governs the generation of the data, just like we are doing always in the Bayesian case. And the algorithm is sensitive to these assumptions. We're going to discuss this at the end today. Okay, and in general, it's a good algorithm in the sense that if you make the right assumptions, it's known to converge to the local maximum of the likelihood function, which basically means that if you do a few restarts, you will always get the local maximum, and in one of them, you hopefully to get a good local maximum, maybe a global maximum. So then we played with this coin as an example, and let me just go to the 3 scenarios that we discussed. So we talked about 3 scenarios. One of them was an easy scenario where I toss one coin 4 times. I'm giving you the outcomes, head, head, tail, head, and I'm asking you which of the 3 parameters that I have is more likely to have generated the data. And you can guess, right? The one that is closest to 3/4 head. Everyone agrees? The second scenario is more interesting. First of all, I toss my coin 0. Depending on its value, I'm choosing either coin 1 and toss it 4 times, or coin 2 and toss it 4 times. And then I repeat. Toss coin 0, depending on the value, I'm tossing 4 times one of the coins. And this is what we get here. This is scenario 2. And again, it's easy for you to see that you can estimate the parameters. Both the alpha, which is coin 0, and the P and the Qs. The interesting one is scenario 3, where I'm doing the same thing, but I don't show you the label, which means I don't tell you every time what did I get with coin 0. I just show you the outcomes, and you know that each 4 consecutive tosses belong to either coin 1 or coin 2, the P coin or the Q coin, but you don't know which one. And of course, this is going to make things more interesting and harder to estimate. Questions? Okay, so this is kind of the way I think about it, you know, and the reason I'm showing it this way is because next week we're going to talk about graphical models, and we're going to see everything that we're doing here as a graph, or we're going to see graph as a representation of these probability distributions. The important thing is that we don't know how to solve scenario 3. We don't know how to solve it analytically and just look at the data and say, these are the most likely parameters, P, Q, and alpha. We have to run an iterative algorithm, and this iterative algorithm has some nice property. Okay, so let's see what we're going to do. So if we know which of the data points, these 4 consecutive tosses, came from coin 1 and each from coin 2, there's no problem. Everyone agrees with that. Basically, that's what we were going to do, right? So remember that under the Bernoulli assumption, if we make M tosses and K of them are head, we know how to estimate the parameters. Also remember that this is under the Bernoulli assumption, right? So I have a specific model that I'm using. Under this model, this scenario is an easy scenario. But we are not under this scenario because we don't know. So what we're going to do is we're going to guess the probability that a given data point came from 1 or 2. Basically, what does it mean to guess? It means to add labels. But we're going to add fractional labels. I'm calling it also fictional labels because they're fictional. But they're going to be fractions just like the one that we discussed 5 minutes ago when I reminded you of the naive-based situation, right? So now that each of these data points, has a label, now the label may not be coin 1 or coin 2. The label will be 0.6 coin 1, 0.4 coin 2, but that's fine with us, right? Now we can continue. We can compute. We can estimate our parameters. We can run the naive-based algorithm for this data, get new parameters, which I call here compute the most likely value of the parameters, as we did in the naive Bayes example. And we can continue. What does it mean? We can compute the likelihood of the data now, re-estimate our parameters, and keep on going. So essentially, we are running the naive Bayes algorithm. And the reason we can run the naive Bayes algorithm is because I'm making this Bernoulli assumption. But the starting point that we have is random. So essentially, this is the game we're playing. We guess labels. We use them to estimate model parameters. Now that we have model parameters, we can compute the likelihood of the data that, yet again, gives us labels, and we can keep on going. Okay, so let's just do this formally. So we are assuming for a minute that we know the parameters. The parameters are p hat, q hat, and alpha hat. So, and we're going to first use it to label the data. Basically, what does it mean to label the data? We're using to decide for a given data point which coin it came from. So once we do this, I'm repeating, we're going to use this label to estimate the most likely parameter, and we're going to keep on going. So here is my notation. We have n data points. We have m tosses each. hi heads in the ith data point that I call di. So given that I guess I have these parameters, alpha hat, p hat, q hat, what is the probability that the ith data point came from coin 1? We're going to call this the expectation step, and you can compute it. So I'm denoting it here, P1i, the probability that the ith data point came from coin 1, or the probability that this data point, di, came from coin 1. And we know how to compute it, right? This is Bayes' rule. It's P of di given coin 1 times P of coin 1 divided by the probability of the data. P of coin 1 is this alpha hat here. That's the guess parameters. The probability that this data came from coin 1 is 1 minus p hat to the m minus h times p hat to the h. Everyone agrees? Again, we have a model. We use the Bernoulli model. That's what we get. And here I'm just normalizing, right? So the probability of the data is alpha times this plus 1 minus alpha with the q's. So I have now the fractional labels. This is P1i, and the second label is 1 minus this. Okay? So I solved the first step. I labeled the data with these fractional labels. Now, I'd like to compute the likelihood of the data so that I can find the parameters, kind of estimate the new parameters. It's the new naive Bayes, the next step of the naive Bayes algorithm. We're going to maximize the log likelihood of the data, of the n data points, which is this, right? So sum over 1 to n, log of the probability of the data given the parameters. The problem is that I don't know the coin's name. So one of the parameters is missing. One of the variables is missing. We're going to marginalize over it. So this is our y here. So really what we're going to do is we compute the sum over the data point, log sum over the values of the y of this variable. Now we see a problem. Because the sum is inside the log, maximizing it, finding the most likely solution is difficult. And this is kind of the technical difficulty in the EM algorithm. We cannot maximize this, and instead, we're going to maximize the expectation of the log likelihood over the coin's names, over the missing variable. So we're going to maximize this, the expected log likelihood, which is the expectation of this variable. I could have put a small y next to the expectation. So at this point, you can either believe and say, okay, that's what we're doing in EM, or you can think about justifications. Why is that what we're doing? Why does it make sense? And there are many ways to justify why is it okay, or at least make sense, to maximize the expected log likelihood rather than the log likelihood. And I'm giving here one explanation. You can forget what I'm saying in the next 3 minutes and just skip to how I'm using it in the next slide, or just believe this explanation. So really what we are doing is the following thing. So we cannot use the standard complete data log likelihood formula. So we're going to use the expectation of the complete data log likelihood under the distribution of y, the posterior distribution of y, in order to approximate it. So specifically what we're doing, we're thinking about this p of di given the parameters, or log p of di given the parameter as a random variable. These random variables can take two values, one with y equal 1, another one with y equal 0. So instead of maximizing the log likelihood, we're going to maximize the average, the weighted average of this random variable relative to y. This really is going to give us a lower bound to the likelihood. And the reason it's a lower bound is I'm writing this here explicitly. So this is really what we want. The log likelihood, which is sum over the data, log of this. Right here I marginalize over the y. I can write this always, this expression here, p of di comma y, as, let's read it right to left, p of y given the rest times p of d given the rest. Now, if you think about it, if this is your random variable, this is the value of the random variable, this is the probability that this value can take value 1 or 0. So really, this is the expectation relative to y of this random variable. So far, everything I've done is right until writing this as the expectation of this random variable. Now, we don't know how to maximize it. So we're going to use an inequality and say, what I have there is log of expectation, right? I have log of the expectation relative to y of something. Instead, I'm going to write it as the expectation of the log. It turns out that that log is a concave function. The log of something, the log of the average is always larger than the average of the log, right? So what you see here, this is the log function. What you see here is the average, weighted average between these 2 points. And the log is always above them. So log of expectation is always greater than expectation of the log. This is something that is called Jensen inequality. And we're going to basically deal with this resulting thing, the expectation of the log, and maximize that. So we maximize the lower bound of the likelihood, and this is why it makes sense. Okay, so let's go back to the, so now that we believe this, we maximize the expectation of this random variable. I basically justify why this makes sense. So that's what we are maximizing, the expected log likelihood, the expectation of sum over all the data, log di given the parameters. expectation is linear, so instead of expectation of the sum, I can think about it as the sum of the expectation. And now I'm going to simplify this random variable. There is a little bit of algebra, which is going to be written later here, to move from this line to the next one. But basically, I can write this as sum all the data points, P1i log probability of di when the label is 1, given the parameters, plus 1 minus P1i log P data, given that the y is 0. Really, if you do the algebra correctly, there is another term here, but we don't care about it because I'm going to maximize this log likelihood later on, and these are just constant. All we have here is the P1i that we already computed. It's a constant, so I don't care about it. So I'm going to eliminate this from my maximization. It doesn't matter when we maximize. Now, the algebra is written here. You can go over it. But for now, let's just understand what we're doing. So we want to maximize the expected log likelihood. I've written the expected log likelihood as the sum over expectations here. That's the important part. And then I split it to two components, one for the case where the y is 1, the label is 1, and one for the case where the label is 0. And I said also that really, if you do the algebra correctly, you'll get another term, but it doesn't matter for the maximization. It doesn't depend on the parameters. Okay, as I said, the algebra is here. Let's skip it and go back to where we are. So we've written the expectation, and we said that this expectation can be written. I'm using here the approximately because remember that I eliminated one term from this thing, so it's not exactly equal, but given that we're going to maximize, it's okay to just replace this term with these two sums. Now everything becomes simple because we can write down these sums. So what are these sums? This is sum over the data point P1i log probability in the case that the coin name is 1, plus 1 minus P1i log probability when the coin is 0. And that these two we can write. We have the Bernoulli model, so I can write this as, again, I have sum over the data points, P1i log of what? What is the probability when the coin name is 1? It's basically alpha, p to the hi, y minus p to the a minus h. And the second one is 1 minus p1i log 1 minus alpha, q to the h, 1 minus q to the a minus h. This part is easy. I'm taking the log here. So I'm writing it now more explicitly. So I get here P1i, log alpha, h log p, a minus h log 1 minus p. This is from the left side. And from the right side, I'm getting the same thing with the q. So it's 1 minus p1 log 1 minus alpha, hi log q, a minus h log 1 minus q. So basically, I've written an expression for the expected log likelihood of the data. Not the log likelihood, not quite the log likelihood, but the expected log likelihood. We agree that it's okay to write this. Now that I have the log likelihood, I can maximize it relative to the parameters. So this is basically the same game that we've written when we computed that we toss a coin m times and we get k heads. The most likely value of the bias of the coin is k over m, right? We've written the likelihood of this, and then we maximized it by computing derivative relative to p, and we found that p is k over m. This is exactly what we've done here, right? So we have 3 parameters in this case. We've written the likelihood of the data, almost. We've written the expected likelihood of the data. because we couldn't write the likelihood of the data. We couldn't maximize the likelihood. Now that we have this expression, we're going to differentiate it relative to the three parameters and find what are the best parameter, the most likely parameter for this. So that's what we're going to do here. So I'm going to take this expression and differentiate it relative to alpha, p, and q. Again, let's look at it. What happens when you differentiate this relative to alpha? From here, everything disappears. From here, all these disappear. So what I'm going to get is sum p1i over alpha minus 1 minus p1i over 1 minus alpha. Let's just go back and check. So from here, you will get p1i over alpha, because I'm differentiating log. And from here, I'm getting 1 minus p1i over 1 minus alpha. If you solve this, you're going to get that alpha is this. Sum over p1i divided by n, which should make sense. Right? What is that? What's the interpretation of this? What is our estimate for alpha? So p1i was the probability that the ith coin was labeled 1. Right? So the sum over this, essentially you're counting how many of the n coins were labeled 1. So it makes sense that this divided by n is alpha. Okay? So this should make sense to you. Interpretation of P and Q is a little bit trickier, but again, you can think about, you can see that it makes sense. So for P, again, we differentiate the previous terms. You can go and check that this is the right thing to do. Here you have the sum of the coins, the sum of the P1i, which is basically the number of 1 coins. And here you have a weighted sum of these probabilities with hi over n. Remember, the hi over m is kind of like the k over m from the simpler exercise that we've done, right? So again, this should make sense as the estimate of the p, and the same thing is going to happen for the q. Questions? Okay, so let me summarize. Again, as a sanity check, I mean, you should think about the weighted fictional points or fractional labels that we talked about before, and this should make sense for you because P1i is really, and 1 minus P1i are really the fractional labels that we've used at the beginning today. Okay, so let me, okay, so one important thing, actually, when you do this algebra, you have to remember that the P1i are constants, right? So we got this expression here for the log likelihood. The parameters that we have here are the alpha, p, and q. The P1i we already computed in the previous step. This is our estimate for the probability that this is the 1 coin or the 2 coin. And it's a constant now. So that's important to realize when you compute these derivatives. And let me summarize. Okay, so 2 summarizations. So one is, what is the algorithm doing? Given the old parameters that we started with, we label the data. What does it mean we label the data? We compute the P1i. That's the label. P1i and 1 minus P1i. Now that we have that, we computed the likelihood of the data and used it to find the new set of parameters. So this goes to your question, why would I get new parameters when I label my 100 examples using the previous model? That's exactly what we've done here, right? So we label the 100 examples with the P1i, and now we recompute the parameters, and we're going to get new set of parameters. Okay, summary. Okay. That's the algorithm. The algorithm has two steps. Step one is the expectation step, which is the labeling step. We just guessed parameters, and using these guessed parameters, we use Bayes' rule to label it. We computed this fraction here, which gives us the fractional labels. Once we have these fractional labels, we computed the log likelihood. I don't write here the whole expression that we got for the expected log likelihood, but from this expression, when we differentiate relative to alpha, P and Q, we get these three estimates, which are our new parameters, and now we can iterate. That's the EM algorithm. Now, as I said, it's a family of algorithms. Here we made one assumption on the probability distribution that governs the generation of the data. We assume that it comes from an alpha PQ family, where each one of them is Bernoulli, and therefore we computed it this way. If you have a different family of probability distribution, you follow the same thing, the same procedure, expectation step, maximization step, only that the formulas are going to be somewhat different. And we're going to show one more example of this. Questions so far? Yeah.
Can you just summarize the assumptions in the approximations we made in the maximization step?
In the maximization step, we made one assumption. Not assumption, just we cheated a little bit. Right? So what we said is that that's what we said. Instead of maximizing the log likelihood, we're going to maximize the expectation of the log likelihood relative to the coin's name. So essentially, we're saying, what is the likelihood if y is 1? What is the likelihood if y is 0? Let's average it.
That is a necessary thing, right? I mean, we didn't have any option other than this.
We didn't have an option. Yeah.
And this can be justified logically.
So you justify using Jensen inequality that really what we were maximizing is not the log likelihood, but rather a lower bound on the log likelihood. That's the assumption. And this can be justified multiple ways. I have a few hidden slides here that justify it somewhat differently, and there's been a lot of literature kind of justifying the same thing. So the EM algorithm historically was suggested in the 70s. What was shown there was shown that actually every step of the algorithm increases the likelihood of the data. Again, going back to your original question about are we going to change the parameter after we use the 100 examples that are unlabeled? Yes, not only we're going to change the parameters, the likelihood of the data is going to increase every time. And therefore, it's going to get to a local maximum. And from that time, people found, one, that the algorithm is very useful. Two, that there are many ways to justify why this approximation makes sense. And what I've given here is one kind of semi-hand-wavy way of doing it, but really, this is a way to justify, just to show that what we're doing is we are maximizing a lower bound of the likelihood, so maximizing a lower bound kind of makes sense. That's the only sort of step that we've done that isn't perfect. It's an approximation, but that's the way the algorithm works. Okay, and again, let's go to the summary. Questions on what we do? Yeah.
So you're trying to figure out coin 1 and coin 2, or which of those 2 coins to assign to the
Yes.
example. But then you use y as 0 and 1, right?
Yeah. So thanks for asking this. So I realized as I was going over it that I changed my notation a little bit. I called it 1 and 2, and then later on I called it 0 and 1. I'm going to change that.
Okay, so basically, like intuitively, what y equals 0 corresponds to coin 1, y equals
Yes.
1.
Yeah.
Okay.
Think about it as the P coin and the Q coin.
Okay.
Okay, but modulo that. Okay, so really, it's a general procedure, and we can write everything in more complex notation, and you'll see it a lot in the literature. So, but basically, what we are doing is we are doing an E step, the expectation step, where we're using the current parameters that we have as a way to label the data, and the maximization step, where we're using now the label data as a way to estimate new parameters. And you can write this many ways, and I don't want to kind of get into more complex notation that we already have. I want to summarize. So, as I said, it's a general procedure. It's not just a single algorithm, but rather a family of algorithms really parameterized by the family of probability distribution. What we've done is the Bernoulli distribution, or if you want, a mixture of Bernoulli distribution, because we had Bernoulli for the P coin and Bernoulli for the Q coin, and they were mixed with an alpha parameters. So when we looked at the data, we knew that it comes from either the P or the Q, and there was a mixture parameter that decided which it really came from, and this parameter was the alpha. That's why we call it a mixture of distributions. So it's an iterative algorithm that was shown to converge to the local maximum. Really depends on knowing or having a family of probability distribution. And it's actually very, very useful in practice. I'm going to comment on it a little bit later, especially when you make reasonable assumptions. It could fail miserably otherwise if you just make the wrong assumption on the family of distributions. Okay, so let's move on to another, yes?
So how would you ever test this? Like, let's say you build your model and you still have no labeled data. How do you evaluate?
Okay, so first of all, you can generate data according to some distribution. Don't show the labels to the algorithm. Run EM and see if it gets it back.
Well, I'm thinking like when you're actually trying to use it in a case where you don't have labeled data, and you're saying it's pretty sensitive to starting parameters, so you might want to run it a bunch of times to see which one maximizes it, but you kind of never know, right?
Well, you do it in exactly the same way you do with any learning algorithm. You must have some data so that you can evaluate on, right? So when you run any of your learning algorithms in the homework, you also have some data that you think about as gold data, and you evaluate relative to it. You'll have to do this here too.
Wouldn't you want to just train on that then?
Well, yes and no. There is always a methodological trade-off here. So on one hand, you want to train on all the data that you have. On the other hand, if you do that, then how do you know how well you're doing? So you always have some.
2 over 0.
Well, you always want to have some set-aside data that will allow you, that will give you some sanity check, and you'll know if you've made some changes in the algorithm, what impact does it have on your performance. So you always have to set aside some development set so that you'll know how well you're doing. This is, the first principle of doing machine learning. And you're right, this is going to cost you a little bit because you didn't train on this development data. Maybe at the end, before you sell your model to someone, you're going to train on that too. But as you develop things and you want to know whether what you're doing improves or not, you want to have this development set, and you don't want to incorporate it into your training data because it's going to deceive you. And the same happens here. I mean, there's no difference. Okay, but I'm going to go back to your question at the end of the lecture today and think about how do you know. Okay, so I want to move to another algorithm. And actually, I think many of you have seen this algorithm before. It's an algorithm that is called k-means. It's a clustering algorithm. Given data points that, again, as before, we know that the data points are generated independently. In this case, I'm assuming they are generated from a mixture, using the same vocabulary as before, of normal distribution, Gaussian distributions. So it kind of looks like this. I have points on the x-axis. I assume that there are, let's say, 2 Gaussians here. But a given point could belong to this Gaussian or belong to this Gaussian, and I don't know which it came from, right? And my goal is to take all the data points and cluster them, essentially tell which of the Gaussian it came from. So anyone knows about the K-clustering algorithm? The K-means algorithm? How does it work?
The integrated algorithm is roughly used to set the center equal to, you're trying to minimize the sort of, the objective function is the distance between the points of each cluster from the center of the cluster, the sum of square distances. And you're trying to minimize that, so every iteration you sort of, I think you set the center of the cluster as the mean of the data points, and then you recalculate the sum of square distances to keep the range.
Exactly. So let's start one step before. How do you initialize the algorithm?
You initialize a random set of clusters.
So you know that you have K clusters. We're going to assume that K is given to us. Someone told us how many clusters are there. And I'm going to initialize with K centers. Once I have these K centers, I'm clustering the data relative to this, which means for each data point, I'm going to say which cluster it belongs to, right? And I'm going to do it in a way that makes sense, that minimizes some sum of square distances. But basically, I'm assigning each red point here to one of the clusters. Once I do this, I can recompute the centers. And now I have new centers, I can redo it again. Right? So again, step 1, choose centers, assign points to centers, recompute centers, keep on going. So that's the standard K-means algorithms, right? So I guess K centers, and I repeat, I place each point in its center based on distance, minimizing distance of some sort. Re-estimate the centers, replace or reassign the points to the new centers, and keep on going. And basically what we're going to do is we're going to refine this algorithm a little bit as an EM algorithm. Really, this is an EM algorithm, only that this is not quite the right algorithm. We're going to fix it a little bit and write it as an EM algorithm. So let's just do this. So just like before, first we notice that had we known that all the data points that we have are taken from one Gaussian distribution with mean mu, finding mu is easy. Finding the most likely value of mu is easy. What would you do? Compute the average. Why?
Assuming that the data points are representative of the Gaussian, so it's equally probable that the left and right equidistant.
Right, so the question that we're asking here, let's assume eliminate one of these. Let's assume you have only one Gaussian and you have red points, and we want to know the mean of the Gaussian. The suggestion here is to just compute the average. And the right answer is because it's the most likely value. And we can, again, just like we did with the coin tosses, we can compute this. So what is the assumption now? We change the assumption. The assumption now, points are coming from the Gaussians. What is the probability of x given mu? It's just this. It's e to the minus 1 over 2 sigma squared. It's a constant. We're going to assume that all the variances are the same. X minus mu squared times some constant outside. That's the probability distribution. So if I have many data points m, I can compute the log likelihood. I'm writing here as ln log with the natural base, because it's going to be easier, of the log likelihood of the data, given that the average is mu. We can compute it this way. We basically take just this part, and we can maximize this log likelihood, which is basically equivalent to minimizing this. The most likely mu is argmin over mu of this sum. We can differentiate it, and if you differentiate it, it will take you a minute to figure out that this is mu, the average. So the average is correct, and the justification that we can give in this class is because it's the most likely value, given this distribution, which basically gives you also a geometric interpretation. It tells you in what sense this center is the best center. It's the best center in the sense of minimizing the square distances, right? So that's what an average does, right? It minimizes the square distances. Okay, so the problem is easy if someone tells us all these points have label mu. Okay, but the problem is that we're not given that. We're given a mixture of mu's, a mixture of k different normal distribution, and we don't know when we look at the data point which mu it came from. Could be mu1, mu2, up to mu k. And that's our problem. Exactly the same thing as the coin, just with a different probability distribution. So just like before, we're going to label them, choose a mu, replace the probability, the points, and keep on going. So the first question we're asking is, assume that we observe a data point. What is the probability that it will sample from mu j? So this is equivalent to the P1i that we had before. Now we're going to call it Pij. And Pij is the probability that it's mu j, given that we observe the point xy. Bayes' rule says compute it as P of xi given mu j, P of mu j divided by the probability of the data. And I'm assuming P of mu j here is 1 over k, uniform distribution. That's my prior over the all clusters. I don't have any better way. If you do, you'll put it there. But so far, I'm assuming that it's uniform. And this is P of x equal xi, given that mu is mu j. And here I'm just normalizing. I know how to write this because I'm assuming it's a Gaussian distribution. So this is e to the minus xi minus mu j squared divided by this constant, and that's my Pij. So now I have these fractional coefficients, fractional labels for each one of the centers. And the next step is going to be to compute the log likelihood of the data, given that I have these labels, and recompute the variables. So in order to do this, I'm going to introduce some notation that is going to maybe complicate it at the beginning, but simplify things at the end. So for each data point xi, I'm defining k Boolean variables, zi1, zi2 up to zik. And the way I'm defining it is such that zij is 1 if and only if xi came from the jth distribution. Okay, so only one of the z I j over all j's is 1, the one that is correct. So I can also write the distribution, the expectation, sorry, of the zij. It's 1 times the probability that xi came from uj, plus 0, the probability that it was not from uj. And it so happened that this is just Pij, right? This is the notation I used before. So Pij, remember I used it in the previous slide as the probability that example xi came from uj, And it's also the expectation of my new variable, Zij. Basically, I just rewrite here the definitions that I showed earlier. What is the definition of expectation, and the fact that it's linear. Okay, so now I can go back to write the likelihood of the data. I'm reminding you that I have my hypothesis, I have my current parameters in H. The probability of the label, given my current parameters, is the same as the probability of xi, given its corresponding zi's. I haven't changed anything. This is just a notation, and I can write it this way. Here is the advantage of using the Zij. I don't know which mu I to write there, right? So I'm basically summing over all the Zij, sum over j Zij, and therefore only one of them is going to survive here, and the rest will become 0. So essentially in one expression, I've including my uncertainty is to, what should I write there? Should I write Z5? Should I write mu5 or mu3 or mu1? Right? So the Zij is just an invention so that allows me to write this even though I don't know which mu to put there. Okay? Because one of them is 1 and all the rest are 0, so it disappears. So now I can compute the likelihood of the data. I have m examples, so I'm summing here. I'm writing directly the ln, right? So I don't carry the e to the power here. It's sum over all the data points. This is the coefficients that I have. And here what I have is this expression, sum over j, Zij. The expectation of this is going to be sum over m. I'm pushing the sum over j, Zij times this. And I can push the expectation inside because expectation is linear. So expectation of the sum is the sum of the expectation. So I can push the expectation inside here. And this guy, we know already what it is, right? So this is basically Pij, as we had in the previous slide. So what did we get? We've written the log likelihood of the new parameters given the old parameters as this expression. Just articulating what is written here. Given the old parameters, h prime, we label the data, right? We computed the Pij's. Now we compute the likelihood of the data. And next we're going to differentiate this likelihood and find a new set of parameters that maximizes this likelihood. So the parameters that I care about are only the mu's. So I'm differentiating this with respect to the mu j's. And I'm getting some constant that we don't really care about, times differentiating this is going to give me expectation of Zij times x minus mu j. The 2 and this goes into my constant here. If I want to equate this to 0, what I'm going to get is this value for mu j. And again, we can think about this mu j and convince ourselves that this makes sense. It's almost the same expression that we had with the coins. Right? The Zij is the P1j that we have, or the Pij if you want. Right? So the sum of this is the number of those data points that came from the jth center, from the jth cluster. And this is a weighted average of these xi's, where each xi has a weight. What is the weight of each xi? Xi can belong to j, but can belong to j equal 1 or j equal 2 or j equal. And this is the weight that is given to xi when it belongs to the jth center, right? So we kind of split xi among all the centers and give a fraction of it to each one of the centers. And this is basically the weight that is given to xi being in the J center. Okay, so let me summarize here and then see what we've done. So we have endpoints. We know that they're coming from a mixture of k distributions. We fix sigma. We're not playing with the standard deviation. We just have as our parameters the k means, mu1 up to mu k. The first thing we're doing is we are guessing for each data point, where is it coming from? So this is essentially the fractional labels that we are assigning. We are saying xi can come from any of the k centers. The probability that it's coming from the jth one is this. We can compute this given our estimates, original estimate for the mu j's, right? So essentially we split the point between multiple centers. Which fraction of it belongs to the J center? It's Pij. Now that we have that, we computed the likelihood of the data, differentiate it relative to the mu's, and got, okay, so the new mu's are going to be this. So it's exactly the same algorithm that we had before. Guess labels, fractional labels, use them to estimate the likelihood of the parameters and compute new parameters. And we're going to repeat this. So what's the difference between this algorithm and the one that we kind of described when we started with? Yeah.
Here we are actually assigning fractional labels for each point. There we were discretely assigning each point to the nearest.
Right. So essentially there we said we're going to look at the data point xi and decide which cluster it came from, which center it belongs to. That's kind of the popular k-means algorithm. What we are saying here, the EM algorithm says you don't need to do this. You don't need to assign in a hard way each data point to one of the clusters. You can split the data point to be P11, it came from the first one. P12 of it came from this one. Py3 came from this one, and so on. Doesn't matter, because you can run your algorithm, your estimation, with these fractional labels, and you're going to get this. So this is the EM algorithm. The other algorithm that we started with is something that is called, in the literature, hard EM, or sometimes truncated EM. In fact, it's a very practical algorithm too. In many applications of EM algorithm, people run hard EM. In fact, many times they will even not tell you. If you follow the literature, they will tell you that they run EM, but they actually ran hard EM. And the reason is that it's cheaper computationally. You don't need to keep all this probability distribution with you when you run hard EM. You just assign it in a hard way and keep on going. But this is really the difference, right? So, and just like I mentioned at the beginning, in what sense these are the k best means? It's in the sense of minimizing the sum of square distances, because this was the probability distribution that we started with. Okay, I'm just putting here the standard k-means algorithm, which I call the hard EM version, so that we'll see the differences. Questions? Yeah.
Three questions. First, does the RDM have convergent identity?
No. But it's actually a pretty good algorithm.
And intuitively, if it were to converge, this subversion would converge faster, right?
Okay, so what happens is that if you don't, and this is actually well known in the literature, studied in many works, if you have good starting point, hard EM is going to be better. If you don't have good starting point, hard EM could deviate quickly from what you want. The real EM is going to gradually improve and will do better. So basically, the bottom line is good starting point, use hard EM. Not good starting point, use EM. And this is true, by the way, not only for this simple model, it's true even for more complex models. Okay, so I want to leave you, this is summary of EM, you can read it. I want to leave you with something to think about in your Thanksgiving break, something that kind of closes the loop on some of the things that we've done. So we have 3 minutes to discuss this. Here's a learning puzzle. Training, a sample of data points, n plus 1 dimension, x0, x1 up to xn. The task, predict the value of x0 given assignments to all the n variables. So in training, I've given you m data points, let's say, like this. And then I ask you, eventually, given an assignment to n variables, given an example, predict x0. What would you do? Okay, excellent. So one simple option is forget what we talked about in the last few weeks. Remember what we talked about earlier in the semester. This is just the standard discriminative learning setting, right? So x0 is the label. Let's call it L or Y. x1 up to xn are the features. Just make it a learning problem. Everyone agrees? Standard machine learning problem. It's the badge problem. It's all the other problems that we've seen. Option 1. Option 2 is to not forget what we've talked about in the last 2 weeks and think about this way. Let's assume that this is how the data was generated. I'm assuming some hidden variable z that take k values, z1 up to zk, with probability alpha z. Sum of the alpha z's is 1. Having chosen a value for z as the hidden variable, I choose values of xi, 0 to n, where the probability that I assign the value xi is piz. Z is the value of the hidden variable. So what you have is this picture. So first of all, I postulated this z at the top. And z can take k values with probabilities alpha z. Given that I chose z equal 2, I'm predicting my xi's with probability piz. And let's assume that this is how I got this training data. Okay? Now remember that your previous protocol didn't make any assumptions. Bunch of data, labels, let's learn. Now I'm saying, you know what, I know something about how the data was generated. This is how it was generated. And this is kind of realistic in many, many situations. Right? So it's really a mixture of probabilities, of probability distribution. Now that I also made this assumption, I have really 2 options. I have let's start with the bottom one, the non-parametric option, which you suggested. Learn x0 directly as a function of the other variables. But I also have the parametric option. I have a model, or assumption on a family of models. I can estimate the model using EM. Once I know the models, I have all the parameters, the alpha z's and the piz's. I can make predictions on any data point that you give me. Right? So everyone agrees that with this, the way I describe the problem, you have 2 options. Right? You have the parametric and the non-parametric. Which one is going to be better? So now I think I'm going back to your question, how do I know it's good? Really, the way I described it here, you can actually compare. I have these two options. So which one is going to be good, better? And it's really an interesting question because in this setting, you can do a fair comparison between these two models. And I'm not going to describe it in a lot of details, but I'm just going to give you two facts. So if k is equal to, what is k? K is the number of values that z takes here, right? So if it's only two options, two coins, two clusters, mixture of two things, then it turns out that x0 in the generative model turns out to be a linear function of the other variables. So you can write x0, or you can write all the xi's are Boolean. So the separating function for x0 is a linear function of the other xi's. This can be written analytically, which now makes for a very interesting comparison. You can run your favorite linear learning algorithms, to learn x0 in the non-parametric case, or you can run EM. And what it turns out that if you know that k is 2, if someone told you the real distribution that generated the data, it's going to do better. EM is going to do better than your favorite linear learning algorithm. Because you actually are doing the optimal thing. You know the probability distribution, you estimate the parameters, you do the best optimal thing. On the other hand, if you don't know, let's assume the data was generated with k equal 5. You did not know, you assume that it's k equal 2, and you ran EM with k equal 2. The learning linearly is going to beat the EM algorithm. Yeah. Yeah. So that's an old paper that basically did a fair comparison, or looking to do a fair comparison between generative and discriminative thing. So, and this is a setting, or one setting at least, where you can do this. And the cool thing, I think, is that we can always ask the question, which one is better? Should we use generative models? Should we use discriminative models, parametric, non-parametric? And the answer is completely unclear because it depends on assumptions that you're making. So here you have a setting where you can actually do something fair, a fair comparison, and you can see what happens. So again, from my perspective, the important thing is that you will look at this setting and you will have these two options. You will be able to see that you can either run a discriminative model if you have no other information, or if you do have other information, or you are willing to make additional assumptions, you can also run generative models. And in life, it will depend which one you're going to use. Non-parametric is much easier to use. Just take out of the box something. You don't have to compute equations and figure out how to estimate parameters. But sometimes the parametric are going to be better if your assumption makes sense. Okay, I'm going to stop here. Final questions? Yeah?
So the hard KV thing, you have a Gaussian assumption, but for the soft thing, you can change the assumption, right?
I can also actually do the hard thing with other assumptions. So whenever you have a soft EM algorithm, you can truncate it. So basically, you have the Pij every time, and you just take the argmax rather than keep them.
But then it won't be the mean, right? The new.
It will not be exactly the right interpretation, but you can always do the hard thing.
But so how you select the cluster centroid after getting all the cluster points, that will also change. It won't be the average.
I think it will be the average.
If it's not centered evenly, it might. Okay.
Okay, we should think about it, but I think it's going to be the center. It's only that it doesn't mean that all points are going to be placed in the same way as in the soft. Okay, other questions? Okay, so have a good break. Happy Thanksgiving. We'll see you next Monday. And I have 2 office hours today and tomorrow for projects.
Yeah, so it's like it's iterated, like it takes me the first, so you have 100 examples, it
Yeah.
takes the first and the active and the parameters. Then like does it like after you estimate, does it reassign label to this first example or it keeps the label?
Oh, it does. It does assign labels to everything. Well, again, you don't have to. You can say, I count on these 10 examples and I'm not going to reassign. But in principle, the algorithm is assuming that none of the data was labeled. I just started with this example of 10 labeled example because I think it's a little bit more intuitive to understand. But in principle, the EM algorithm assumes that none of the example is labeled, and it's going to assign to all of them.
So every time, like after every iteration, it's reassign
Yes.
label to everything.
Right.
Okay, thank you.
Fine.
So for the EM algorithm, do you repeatedly random assign the beginning labels? Like
Just once. I have to assign only once.
why?
Because once I assigned it, I estimated the parameters, and now it's not random anymore. So let's think about the naive base case. So I assign the labels to each example randomly. Now I compute the parameters. Now the parameters allow me to reassign labels, right? Because I can compute the most likely parameters, so I can predict, which means I can assign labels.
In K-means, you also can reassign the labels, but you also need to randomly assign, run many times to randomly assign.
No, only first time I do it randomly, right? So in K-means, at the beginning I chose samples. Now that I chose the mu i's, the mu j's. Given that I have the mu j's, I computed the pij's, which are the fractional labels, right? From that point, I never guess anymore, right? So now I have the assignments of the points. Each point belongs, this point belongs a quarter to here, a third to here, a quarter to this, and so on. And given that, I can recompute the mu j's and do the reassignment, recompute the mu j's, do the reassignment, and so on.
Yeah, I mean, for the final decision, will it be influenced by the first what you random assigned, or it will not?
It will be.
So will you try many times?
Right. So as I said in one of the slides, EM is sensitive to initial parameters, initial assignment. So K-means is just an EM algorithm.
Okay.
So yes, it will be sensitive, and in principle, the way people run it is they will initialize multiple times. So they initialize, run the algorithm, look at what they get. Initialize again, run the algorithm, look at what they get, and eventually choose which one they want. So that's kind of a standard way of using the algorithm.
So for the EM, how do you decide when we stop it?
Okay, so you have 2 options, right? So you can compute the likelihood of the data, right? That's a well-defined thing. That's one. 2, if you have a data set that is labeled, you can compare how well you're doing on that. Right, so you have these 2 options. We probably will not talk about this, but there are standard ways of stopping criteria for K-means. basically they have to do with computing the likelihood of the data. Right, so you have some expectation from the behavior of the clustering algorithm, and that's how they do it.
So like a threshold when the likelihood.
Yeah, it has to do with the threshold, right? So basically you can compute the average. You can compute some parameters on the clustering algorithm. So how far are the centroids from each other, for example, and how compact each cluster is, and you can write some objective function that take these two into account and use it as a stopping criterion. Yeah. But essentially, it boils down to computing the likelihood of the data relative to your current set of parameters. There is a guarantee of convergence to a local maximum, not to a global maximum. On their,
Or they all have
in fact, I think it's only under correct assumptions. Yeah. So you could diverge if you don't make the right assumptions. Yeah, but the algorithm is relatively robust, I think, in practice. So if you, but again, you can make very bad assumptions that your data doesn't correspond to, and it's not going to be good.
so most time it's
So